In this fourth ghost lecture, we specialize everything to Hermitian matrices. So we have perturbation results for Hermitian matrices. I mentioned in the previous lecture why things are easier here, but let me say it again. Things are a little bit easier here, and also we should expect better results. We know that Hermitian matrices in particular are normal, and one of the things that we've been seeing is that normal matrices are more stable to perturbation. But they're easier. Why? Because if any matrix is Hermitian, then we know that there is a basis of, in fact, an orthonormal basis of eigenvectors, which means that no matter what m is, so if m is equal to a, or if m is equal to a plus some perturbation, then there's always going to be a one-dimensional, two-dimensional, three-dimensional, any dimensional I want invariant subspace, because it's Hermitian. So we no longer have to prove that there exists an invariant subspace. So we can skip that part and just move directly to bounds. So there's some other things also that that happen that will make our life easier. Just writing what I said. We no longer need extra conditions to guarantee the existence of an invariant subspace. So as I had suggested that you do as an exercise in the previous lecture, you can think about it. Find a matrix A that has, say, a two-dimensional invariant subspace, but even a small perturbation of that no longer has a two-invariant subspace. So the point is that that cannot happen for Hermitian matrices. And because of that, the research that and the work that's been done one direction is called direct bounds. And they're direct because they don't have to focus on existence, just on bounding the distance of the subspaces. And much of this work is due to these two people. So we'll present a subset of the work. Okay, so some other things happen that make our lives a bit easier, and this relates to. You should contrast this to the last result that we mentioned at the end of the third lecture in this little series. If two matrices L and M are Hermitian, and I'll stop writing this in this lecture because everything I'll talk about is going to be Hermitian. Then, if we define the step using the Frobenius norm, in other words, if this is defined as the infimum over all Frobenius norm 1 matrices of T of Q measured in the Frobenius norm, this satisfies, this is equal to the smallest eigenvalue. And this takes a little bit of work to show, so we're going to skip the proof, but just contrast this with the last result that I gave at the end of the last lecture, and also the exercise that I put there, which basically showed that, so the result showed that there's an inequality for general matrices here, using any consistent norm, including the Frobenius norm, which we know is consistent. But the exercise that you did at the very end shows that there can be a big gap here. Whereas here we see that if there is a good separation between eigenvalues of L and M, then SEP is also going to be big. So that was not the case. Okay, so now let's move to the direct bounds. Again, if everything in sight is Hermitian, so it is Hermitian, and suppose that x1 x2a times x1 x2, where this is unitary, is equal to L1 0 0 L2. Okay, so note again that this is something that doesn't happen for general matrices. If in the Hermitian case, if we have an invariant subspace, then we know that its orthogonal complement is also going to be invariant, and that's why I'm able to write it write this result in this way. That's why we have zeros not only there, which we always have for an invariant subspace, but we also have a zero there as well. So what we know is that x, which is equal to the range of x1, is invariant. Now, what I want to know is the following. So suppose we have a matrix Z, which is the same dimension as x1. And it has orthonormal columns. Orthonormal. So what I want to know is what can I say about the range of Z compared to the range of x1? So how close are these two subspaces? So the general question I want to ask is how close is the range of Z to the range of x1? But we'll answer this in a little bit more detailed way. So let M be any matrix. I guess it would be helpful if I wrote some dimensions here. So let's suppose that x1 and Z both have k columns, and let's let M be any k by k matrix. What I'd like to know, and let's write, and so what I'm thinking about M is an approximate representation of A on Z. Okay, so remember that that since x1, okay, so what am I trying to say here? Let me draw a brief parenthesis. So recall that because x1 is A invariant, we know that A of x1 is equal to x1L. Another way to write that, of course, which is what we've been doing, is that ax1 minus x1L is equal to 0. But the point here is that L is an approximate, it's nothing approximate, is the representation of A on the range of X with respect to the basis of X1. Okay, so now let's suppose that this is what happens when both L and when we look at an approximate version of this. So an approximate version of this means that we have A times Z. Z is taking the place of x1. minus z times m. M is taking the place of L here. Let's suppose that this is not equal to 0. If it were equal to 0, we would know that the columns of Z span an orthonormal subspace, an invariant subspace, and M is a representation with respect to Z. So instead, let's suppose that this has some residual R. Okay. So then this the question is, how close is the range of x1 and the range of Z as subspaces? So note that we're essentially defining a perturbation. So this is like defining a perturbation E that's equal to n minus L1, something like that. That's what we're at. Okay. But okay, so what do we want to know? Again, let me just briefly summarize what we had in the previous on the previous page. We have x1, x2, and x1, x2 is equal to L1, L2, and we have that A Z minus Zm is equal to R, where Z is same dimension as X. So let's also let delta equal to the minimum of L2 minus M, and assume that this is greater than 0. Then, the theorem says that I'll explain what this notation means, but I think it's fairly self-explanatory. Then we have this bound. So what is this? What is this matrix? This is a diagonal matrix with the canonical angles between the two subspaces, range of x1 and the range of Z on the diagonal. So basically, all this really is the square root of the sum of squares of the sines of the canonical angles. And we have a bound. We have a bound on this. So the proof of this result is pretty straightforward. So let's give it everything that we've seen. So we have that R is equal to AZ minus ZM by assumption. And so this implies that x2 times R is equal to x2 times AZ minus x2 times ZM, which is equal to L2 of x2 Z minus this. So note that we needed the Hermitian matrices, the Hermitian matrix assumption in order to get this equality. Well, not that assumption. After we have the form of A. So in other words, we needed what we used here was this, and namely the fact that the complementary subspace is also invariant. So that's what does not generically hold. So what do we have here? This is equal to L2 times x2z minus x2zm. So in other words, this is just my t operator defined on matrices L2 and M on the matrix x2z. Okay, so this is something that we have that's going to help us bound control R. So recall that delta, which is equal to the separation, we're using the Frobenius norm between L2 and M. This is defined as the infimum over all Q equal to 1 of T of Q. And therefore, in particular, this implies that for any matrix, T of Q is bigger than delta times Q. This is Frobenius norms. So this is true for any Q. This is an immediate implication of the above. So what are we going to apply? So let's let Q equal to x2z. So what does that tell us? That tells us that delta times x2z is less than or equal to T of Q. And therefore, this tells us that x2z, again, all of these, the Frobenius norm everywhere here, is less than or equal to, I'm using the chain of inequalities, of equalities that we had here, is less than or equal to the Frobenius norm of R divided by delta. So why is this basically, why are we done here? So recall that the singular values, so we've done this several times before, but it's a critical point. So let me be clear here. So what are we using? What is this here? So I want to know how close R of x1 is with R of z, and we have seen in the past when we discussed canonical angles that if I look at the matrix that's x2, so this is something that spans the orthogonal complement of R of x1 times z. This matrix, the singular values of this matrix are the signs of the canonical angles between the subspaces R of x1 and R of z. And therefore, the Frobenius norm is just the sum of squares of the singular values of this matrix. We just said that the singular values are the signs. So this is exactly equal to what we want. This is exactly the diagonal matrix that has on the diagonal the signs of the canonical angles between the range of x1 and the range of x2. And so basically what we just proved is the result of the theorem that we have this bound. So that concludes the proof of this theorem. So once again, what did we just prove? We just proved that if R is equal to AZ minus ZM, then we bounded how close Z is to the invariant subspace of A. So we showed that sign that this is less than or equal to the Frobenius norm, where delta, because we're using the Frobenius norm, delta is equal to this, which, as we didn't prove but we stated, is actually equal to the smallest eigenvalue of t. So, when is this useful? Well, there's sort of a generic answer. Because we're using the Frobenius norm gives a bound in terms of it doesn't tell you anything about individual singular values. So in particular, it doesn't tell you anything about individual angles. So if the dimension of x1, and therefore of z, is small, this result can give useful bounds. But, I mean, this is a generic statement. If the dimension of x1 is large, then we are getting less refined bounds, because the Frobenius norm becomes large. So we could have a large Frobenius norm even if each individual angle is actually small. And so as the dimension of x1 goes to the entire space. So this is a great result to use if you're just interested in bounding one or two dimensional invariant subspaces and understanding how those change. In particular, if you want to know how an eigenvector changes, this is a great and powerful result. So in the extreme case, if the dimension of x1 is equal to 1, then everything is one-dimensional, and then the Frobenius norm is equal to the operator norm. But suppose we have for large-dimensional invariant subspaces, what would we like? We would like results in terms of the operator norm, not the Frobenius norm. And it turns out that we can't get this for free. So for this, we need further restrictions on exactly how the eigenvalues of L2 and M are separated. So it's not enough to assume just that the separation is significant. So for operator norm bound, this assumption is not enough. So let's turn to this. Let's turn to this now. The first thing we need is the following lemma. Let's let this be any consistent norm that satisfies the following. A is less than alpha. The inverse is greater than alpha plus delta for some delta greater than 0. So if that's the case, then if ax minus xb is equal to c, then x is less than c over delta. So how are we going to use this? Let me give the proof first. So by consistency, we know that ax is less than the norm of a times x, which is alpha x by assumption. And similarly, we also know that xb is greater than alpha plus delta times x. Okay, so note again that in order this is why I needed that inverse result, because otherwise the submultiplicative property would be giving me the wrong inequality. So then, if we plug this into c is equal to ax minus xb, I get that the norm of c is certainly greater than the norm of bx minus the norm of ax, which is greater than delta times x, just by using the above. And so the result is quite simple. But how are we going to use this? Note that we had a very similar thing in the previous theorem. We had r was equal to ax minus what do we have? Az minus zm, and we were using the bound on the norm on r. So here we'll need to translate the lemma's assumptions on A and V into eigenvalue conditions. So exactly in the same context, as in the previous sine theta theorem, let's suppose now that the spectrum of M is contained in the interval alpha beta, and for some delta greater than 0, let's suppose that the spectrum of L2 is separated in the following way. So it's contained in R, so in other words, if this is alpha plus beta, the spectrum of L2 is here, and then the spectrum of M lies in here, and then the spectrum of L2 is restricted to lie outside. So note that this is again, we have a separation. So delta is again going to be bounded by the separation between the eigenvalues of L2 and the eigenvalues of M, but we have more here. So we have some more specific structure. So, but the above represents an additional assumption. Last time, last theorem only had this. Okay, so so the conclusion here. This is kind of a parenthesis here explaining what that means. But if this holds, if we have this interval condition in this separation, then, and note that we haven't brought up any specific norms here. Then, for any unitarily invariant norm, so for example, the operator norm, which I guess in the past I've denoted like that, or the Frobenius norm, but it was the operator that was our main motivation. We had the Frobenius norm in the previous result. What we care about here is the operator norm. So then the sign is less than the norm of R divided by delta. Okay, so if our norm here is the operator norm, what's the operator norm on a diagonal matrix? It's basically the largest element on the diagonal in absolute value. So what this means, then this theorem says that that the sign of the largest canonical angle is less than the operator norm of R divided by delta. Okay, so this gives us much finer control when we have a large subspace. Okay, so let's quickly give the proof of this. So check that without loss of generality, we can assume that the interval is centered around 0. So we can assume that alpha equals minus beta, and therefore that the eigenvalues of M are contained in the interval minus alpha to alpha. And also this means that the eigenvalues of L2 are therefore contained in minus infinity to minus alpha minus delta union alpha plus delta to positive infinity. So now let's apply the lemma from above. So to apply the previous lemma, note that M is now bounded by alpha, and L2 inverse is bounded below by alpha plus delta. So similarly to the proof of the previous sine theta theorem, we know that since x1, x2, x1, x2 is block diagonal, O1, 0, 0, L2, remember this was a key step that we used in the previous theorem, and R is equal to AZ minus ZM, we we argued that x2 times r, this is equal to x2 az minus x2 zm, which is equal to L2 times x2z minus x2z times m. And now we can apply the lemma above. Using the operator norm, which is consistent. And this gives us that x2z in the operator norm is bounded by x2 r divided by delta, but the operator norm is unitarily invariant, so this is therefore equal to just r divided by delta. So in other words, we have the conclusion of the theorem. Now you can see why we needed that step on unitarily invariant norms. We just need it for this step. The last two results have been stated in a sort of a strange way because it makes them more general. So the last two results have been stated in terms of any z and m. So we don't even know that z and m necessarily have to be related. Of course, the closer they are, the better bound we get on R. But let's look at essentially a corollary of these results to a more direct matrix perturbation setting. So let's apply the above sine theta theorem directly to perturbation. So let's suppose, and this is really going to be the setting that we're going to use when we circle back and look at spectral clustering. Suppose that M and a perturbation of M are both Hermitian. So because they're both Hermitian, we can write that M is equal to x1, x2, m0, m1, x1, x2, and possibly for some different basis, m plus delta is equal to y1, y2 times m0 hat, m1 hat, y1, y2. Where we have that just the magnitude of delta is given, and where we have a condition on the spectrum of M0. This is contained in some interval AB, and also the spectrum of M1 hat is contained in minus infinity A minus delta. B plus delta plus infinity. Again, the basic question is, let's compare invariant subspaces. So what are the two invariant subspaces we want to compare? The invariant subspace of M that we want to compare is X, which is the range of X1. And similarly, the invariant, so this is M invariant. And we want to compare it to script Y, which is the range of Y1, which is M plus delta invariant. We want to know how close are X and Y. So let's let R equal M Y1 minus Y1 M0 hat. Okay, notice that this is exactly the framework that we had in the previous theorem. But we don't want to settle for something that's on the size of R. R is not something that's given in the theorem, so we can come up with a bound for that. So how big is R? R is equal to my1 minus y1 m0 hat, which is equal to m plus delta y1 minus y1 m0 hat minus y1 delta. And this is less than or equal to m plus delta y1 minus y1 m0 plus y1 times delta. And this is equal to 0 plus delta. So therefore, just applying the above result directly, we get the following conclusion, namely that the largest singular value between x and y is bounded by delta over delta. Okay, so the proof of this is essentially immediate, but to understand the connection to the previous two theorems, just plug everything in, and so that the connection is absolutely clear. So this essentially concludes the main results that we're going to give on matrix perturbation for now, and we'll be able to apply this directly to our spectral clustering.